Welcome to the lesson on high voltage systems. This lesson aims to provide a comprehensive understanding of high voltage, abbreviated as HV systems, within the context of battery electric vehicles. We will define HV systems and explore their significance in powering BEVs, emphasizing their role in energy storage, distribution, and propulsion. A key focus will be the comparison and contrast between HV and traditional 12-volt systems, highlighting differences in voltage levels, components, functions, and applications. We will identify essential HV components while gaining insights into their respective functions and contributions to BEV operation. The lesson will also explain the advantages of HV systems, including faster charging capabilities, improved thermal management, and enhanced regenerative braking efficiency, among others. Safety protocols and standards pertaining to HV systems will also be emphasized, covering aspects such as isolation monitoring, ingress protection, and compliance with industry regulations. Additionally, we will explore future technologies in high-voltage systems. In battery electric vehicles, high-voltage or HV systems include various components typically operating at voltages exceeding 60-volt DC and 30-volt AC, with many ranging between 200 and 800 volts DC. These systems are specifically designed to manage the storage and distribution of energy required for BEV propulsion. One distinctive feature of HV systems is the use of orange-colored wires, facilitating easy identification and ensuring safe handling. HV systems form the backbone of BEV powertrains, enabling efficient energy conversion and propulsion while adhering to strict safety standards and protocols. Presented here is a table that compares and contrasts the key characteristics, components, and safety aspects of the high-voltage and 12-volt electrical systems in electric vehicles. The high-voltage system, typically operating at 400 to 800 volts DC, powers the main propulsion components, including the battery pack, inverter, and electric motors. This system uses orange high-voltage cables and requires extensive safety protections for isolation, grounding, and interlocks. Charging the high-voltage system is done directly from the grid. In contrast, the 12-volt system, operating at around 12 to 14 volts DC, powers auxiliary vehicle systems such as the starter, lights, infotainment, and power windows. This system uses regular low-voltage wiring, basic insulation, and fusing, and is connected to the vehicle chassis. The 12-volt battery is charged by a DC-DC converter from the high-voltage battery. Let us now take a look at the various high-voltage components in an electric vehicle that work together to power the vehicle's propulsion. They are the high-voltage battery pack, electric drive motor, inverter, DC-DC converter, charging port, and onboard charger. These components are interconnected by specialized HV wiring and connectors designed to safely handle high voltages. Additionally, comprehensive safety systems are integrated throughout the HV system to protect against electrical hazards, monitor system integrity, and ensure safe operation. The high-voltage battery pack serves as the primary energy storage unit, storing electrical energy in high-voltage form. It then distributes this energy to various components, including the electric drive motor, which is responsible for converting the electrical energy from the battery into mechanical energy to drive the wheels, enabling vehicle movement. Another critical component is the inverter, which plays a dual role in the HV system. It transforms the direct current from the battery into alternating current for the electric motor's operation, and during regenerative braking, the inverter converts AC back to DC, allowing the vehicle to capture kinetic energy and store it back in the battery. The DC-DC converter serves as a vital link between the high-voltage DC from the high-voltage battery pack and the vehicle's traditional 12-volt systems and accessories. It steps down the high-voltage DC from the battery pack to a lower voltage suitable for powering lights, infotainment systems, and other onboard electronics. The charging port and onboard charger are responsible for managing the vehicle's charging process. The charging port interfaces with external charging stations, while the onboard charger converts incoming AC to the HV-DC needed to charge the battery effectively. HV wiring and connectors are specialized to handle the high voltage and current levels present in the system, ensuring reliable power distribution without compromising safety. Finally, safety systems, including contactors, fuses, and isolation monitoring systems, are integrated into the HV system to protect against faults and ensure safe operation under all conditions. High voltage wiring and connectors are specialized to handle the high voltage and current levels present in the system, ensuring reliable power distribution without compromising safety. Finally, safety systems, including contactors, fuses, and isolation monitoring systems, are integrated into the HV system to protect against faults and ensure safe operation under all conditions. Battery electric vehicle components mostly operate at high voltage due to various advantages. The most noticeable benefit is significantly faster charging times. Imagine spending less time tethered to a charger and more time on the road, all thanks to the ability to transfer power at a higher voltage. But HV systems go beyond just speedy charging. They also allow for a lighter wiring harness. Since HV systems use lower currents to achieve the same level of power, thinner cables can be used. This translates to a lighter car overall, which can contribute to a longer driving range. Additionally, HV systems reduce the need for complex cooling systems. The lower currents flowing through the wires generate less heat, making thermal management more efficient. This is a win-win, as it saves weight and improves overall system efficiency. HV systems even enhance the effectiveness of regenerative braking. With a higher voltage system, BEVs can capture more of this energy, translating to a greater increase in driving range. We shall now take a look at the safety procedures, standards, and protocols for high-voltage systems in electric vehicles. These protocols and standards are designed to protect passengers, service personnel, emergency responders, and the vehicle itself from electrical hazards. These protocols cover design, manufacturing, operation, maintenance, and emergency response aspects. Here are some key safety protocols and standards. Isolation monitoring is the continuous monitoring of the electrical isolation between the high-voltage components and the vehicle's chassis to detect any insulation failures that could pose shock hazards. High-voltage components must have ingress protection, abbreviated as IP ratings, to prevent water and particle intrusion. Interlocks are safety features designed to ensure that high-voltage circuits are de-energized when connectors are disconnected or when protective covers are removed during maintenance. Cables must use insulation rated for the high voltages. Thermal sensors help monitor for overheating and damage. High-voltage components and cables are often color-coded, usually orange, and clearly labeled to warn of potential electrical hazards and to facilitate safe handling and maintenance practices. We will now discuss two of the main safety features in high-voltage systems, one of which is isolation monitoring. Isolation monitoring is a critical safety system in electric vehicles that continuously assesses the electrical separation between the high-voltage system and the car's chassis. This system operates by applying a small DC voltage between the HV components and the chassis, then measuring the resulting current flow. Using Ohm's law, the system calculates the isolation resistance. A high isolation resistance value indicates proper separation between the HV system and the chassis, ensuring safety. If the resistance falls below a certain threshold, the system triggers an alert, prompting appropriate action to maintain the vehicle's electrical safety integrity. Another main safety feature of HV systems in BEVs is the high-voltage interlock loop, abbreviated as HVIL. A basic schematic of the interlock loop in an HVIL connector is presented here. Operating as a circuit breaker, the HVIL continuously monitors the integrity of high-voltage connections within the vehicle. This includes a low-voltage loop that precisely checks all high-voltage connectors and components, providing real-time feedback on their status. In the event of loose, disconnected, or damaged high-voltage connections, the HVIL promptly alerts the driver, preventing potential hazards and ensuring the safety of both occupants and surrounding environments. Moreover, the HVIL serves as a fail-safe mechanism, automatically shutting down high-voltage systems to prevent electrical hazards or accidents. Vehicle systems must meet electrical safety standards such as ISO 6469, SAE-J 1766, CFR Title 49, Part 571, depending on the country of sale. These specify many of the safety standards requirements. Specialized training programs by BEV manufacturers train the emergency responders and service technicians on how to safely handle BEVs equipped with high-voltage systems, including safe deactivation procedures and emergency response to accidents involving BEVs. Crash safety standards require the battery and electrical system to be able to withstand crash forces. Deformable barriers help to absorb impact and prevent substantial damage. Visual indicators show if high voltage is present and if the system is active. This prevents accidental contact during regular servicing or maintenance. Let us now explore some emerging high-voltage technologies that electric vehicle manufacturers are developing for future implementation. Next-generation BEVs would likely provide optional 800 or 900-volt systems along with the common 400-volt systems. This higher voltage for lower current for the same power reduces cable sizes and weight, thereby improving efficiency. Electric motors will be integrated into the wheel or transmission, eliminating separate drive units. This simplifies the system, reduces weight, improves response, and eliminates high-voltage cabling. Future solid-state lithium batteries will likely operate at over 800 volts inherently. This would remove the need for boost converters and simplify the battery architecture. BEVs will be able to put power back into the grid using onboard high-voltage systems. This would enable vehicle-to-grid integration for demand response and renewable integration. Advanced converters that have switching frequencies of over 100 kHz are much faster than existing devices. This would allow smaller, lighter, and more efficient converters to be used in BEVs. Inductive charging pads will allow wireless charging and eliminate physical cable charging connections. However, high-power wireless charging still requires special safety considerations. Let us now summarize what we have learned in this lesson. High-voltage systems in battery electric vehicles typically operate between 200 to 800 volts DC, providing propulsion power to the vehicle through components such as the high-voltage battery pack, electric drive motor, inverter, and DC-DC converter. The advantages of HV systems include faster charging, lighter wiring harnesses, improved thermal management, regenerative braking efficiency, and extended driving range. To ensure safety, HV systems incorporate isolation monitoring, ingress protection, safety disconnects, and wire insulation, and comply with national and global standards. Future technologies in HV systems include higher voltages between 800 and 900 volts, further lowering the current and weight of the wires, integrated motors directly connected to wheels, solid-state batteries, bidirectional charging, and the potential for wireless charging. Thank you.